Test. Check it works. Hello, Spencer. Hello, Connor. Good evening. Yeah, Zoom doesn't want to accept this camera. Okay, so let me know if I need to stop sharing screen, but I plan to share it most of the time. I see someone else. No, only two are connected. So here are the okay. So here are the subjects that we are going to present, and on the previous slide is basically the same, just in a more loose way. So it seems that we have covered the principles, momentum operator, and evolution operator. I can go over them quickly, but they are available in the recordings. Okay. So conversion of operators between momentum and position is a really hard time, and since Zane was visiting it last time, you should be in person. You should be the optimal candidate to present it. The computation of operators show it, and making videos and uploading to YouTube, it's kind of the easiest possible. But it's kind of a piece of cherry on the cake after you do hard work on conversion of operators between position and momentum. So let me double check. We have Spencer and Connor, so as a target audience. So I will make sure that your subjects are covered at first. The thing that August placed as a first choice, quantum dynamics of an electron, initial conditions will function as Gaussian. It was covered. Alternative methods, it was not covered, but I have to speak about it. We need to do this, commutation of operators, and this one I will just quickly repeat. Jared, normalization. Discrete representation was done. Normalization was not done, so I need to do this blue stuff. This is unknown presenter is a very easy thing. It is like 5 minutes. Spencer, visualize real and imaginary part of wave packet. I didn't show it, but it is like easy piece of candy. Visualize potential probability distribution. Why there are 3 of them? I wonder too, but it should be easy. Visualize any observable. Yeah, this is Spencer. You did a perfect choice. This is quite easy but important stuff, and it would take me longer to express previous section 5, how to accumulate observables, and then after them it will be natural continuation to show how to visualize it. Computation of expectation level positions of momentum. Those are quite easy. They also follow from here. And Spencer already selected number 6. The last stuff is also just changing one line and rerun the code. Changing the line once again and rerun the code. It's a last thing to do. Yes.
Number 2, is it commutation?
Yes, commutation. Yeah, not computation. It's commutation. And this is also quite challenging stuff. So probably I need to go over the first thing really quick, and then I'll go to commutations. So I hate my ugly writing, but I don't have another one. And probably it would be more reasonable just to write from scratch. So principles of wave packet propagation. Our goal is to go, so I'm speaking right now intentionally for corner. Our goal is to go from past to the future, and we need to move our wave function from past to the future. This means we have wave function at time t, and here we have wave function at time t plus delta t. In order to do so, one can multiply the function by the evolution operator. So in some sense, it is an answer to the first question. Principles of wave packet propagation. Now, next thing, momentum operator. If you want to implement Hamiltonian Wishes operator, it typically has momentum, kinetic energy is momentum plus potential. So potential is kind of trivial stuff, but momentum is derivative operator. So we do need to express derivative operator in so-called finite difference. Finite difference. Let me browse forward through the slides. Last week, I believe I was scratching it. This one is okay. Maybe I did a little bit better. Okay, so it is not perfect, but it has main idea. So I am speaking intentionally for corner. So feel free to. I'm not sure if the sound is working, but type questions or contact me by any means if you want me to repeat something. So maybe call. I will unmute the cell phone. So, wave functions, and I'll try to use older scratching here. But if you guys do not like it, I can redraw and try it better. So if we are doing computer simulations, we do not have mathematical functions. We have wave functions stored. I'm looking now at the box. Saved as value of function at value x equals 0, x equals delta x equals 2 delta x. So as a set of discrete values. And the goal is to implement the momentum operator, which is derivative. In this representation, the derivative, by its definition, is increment of the function as a ratio to increment of the position. And this psi of x plus delta x minus psi of x, you'll be just subtracting two nearest neighbors. And we need to do it continuously to compare each pair of nearest neighbors. Let me check in the chat if corner is okay. If corner is okay for this, yes. Okay, I'm continuing, but I'll try to check again because it's important. Now, if I want to create a vector of numbers which will contain the result of acting of momentum operator onto wave function, which is already in discrete representation. It means that each element will be like subtraction of the first wave function minus zeroth wave function, subtraction of the second minus first, subtraction of the third minus second. So subtracting nearest neighbors and dividing them by increment. I want to build a matrix that would act on the vectors of the elements of wave functions and practice the subtraction of the neighbors. So if I want to subtract first two nearest neighbors, I can select elements of this matrix as -1 and +1. And if I practice row by, and then zeros everywhere else. If I practice row by column here, first element is multiplied by -1, second element is multiplied by +1. So then I will obtain psi of delta x minus psi naught. Then I can put the all factors up front. If I want to get the second element, then I will have the same elements -1 and +1, but not starting from the beginning of the row, but offset by one element. So element number 2 will be -1, element number 3 will be +1. And if I practice it in the way row by column, the first element will be not taken into account. This second element will come with minus sign, and this element will come with plus. So I will get psi of 2 delta x minus psi of delta x. And then if I continue this progression, I will put -1s on the main diagonal and +1s on the upper subdiagonal. So this matrix here will be numerical implementation of momentum operator. And by the way, I'll put a little +1 at the corners for periodic boundary conditions. Let's check. Connor, if if you want me to describe anything in more details, let me know. More details 1, more details 3. No questions. I'll continue. Momentum operator Hamiltonian. So after we did define the momentum operator with final differences, we just plug it into Hamiltonian. And as soon as we define the Hamiltonian, we can plug it into the evolution operator. So this stuff here is evolution operator. And then we do repeat this operation. I'm out of good colors. This operator in the circle again and again at each time step. So basically, I'm done with number one. We do need lines in the code that practice this stuff, and this would take a little longer. But please try to run, download the code and make sure that they are running. Oh, someone else connected. They. Oh, okay. So you get double amount of information. Huh? Yes. So just Spencer and Connor, well, and Zane as well, just practice making sure that the code is running. I will not be able to remind it all the time. Just try to run and see what happens. And if it runs well, it will show maybe close all this figure Windows. Okay. Now, if I'm in the MATLAB and I do have this wave packet free commanded version, I click run. I see this image, which is our Gaussian wave packet. Then I push a tab, and it progresses forwards in time, moving. Center moves forward with small velocity, and the width is increasing this time. So basically, it is what the code is doing, and then there is a popping up several windows that represent the results of this little calculation. So whoever presents the methods may want to show lines of the code responsible for this activity. So for corner, let me go to the right line. So whoop means we go forward in time. The line psi2 equals g tau times psi2 is literally, I'm going back to the PowerPoint, is literally this encircled equation. So psi2 before and after, and this is g tau operator. So it is line number 172 in the code. And then it is repeated again and again, and then this psi2 is processed. Like next line is stop. 172. So next line is just probability distribution of a function absolute value squared. Okay, Connor, I think I'm done with your subject, and now I'm going to Zane commutation of operators. Maybe before I need to do a little disclaimer. Alternative methods to compute quantum dynamics. So luckily it will be done by August. You do not need to do it, but I'll quickly cover it. So when you were watching how the movie is progressing forward, you see that it's kind of duplicated in two lines. So we are practicing fair science, and we need reference point. What if the method we use fails? What if we do not have literature or experimental results to prove that we are doing the right thing? How to prove that we are on a good way? We can compute the same thing with slightly different method and see if they agree quantitatively or at least qualitatively. Therefore, just like if these two lines will diverge substantially, it means we are doing something wrong. If they are qualitatively similar, it means we are doing good. So this probe 2, psi2, gtau2. Oh, and I have forgotten to find what it is defined in the previous line to be complete for the corner. Yes, here, line 112. So matrix exponential, Hamiltonian, number 2, and then Planck constant and increment of time. And the Hamiltonian is just px squared divided by mass plus the potential. The way how the momentum is defined is, I just covered it, and the main principle stays the same. Zane hopefully will tell a little bit more details about going back between position and momentum representation, how later, like explaining this line 108, which looks simple, but there is a lot of hard stuff behind it. Just in case, if this method fails, we may redo dynamics. As you already saw, there is another line where the Hamiltonian is defined in a similar way, but the momentum is defined in a different. So we will call it Hamiltonian 3 and G tau evolution operator 3. So this is encoded in lines from 122 to 126. And each year I'm reading what is this TOEPLITS triplets matrix, but every year I'm forgetting. Whoever needs to present it, like August needs to look through MATLAB help. But this px third method or p squared third method slightly redefines the way how momentum operator is defined in position space, and sometimes, and they give similar results if everything goes as needed. Now, let's check. First, let's check which variables do we have. So I type who, and it shows a big zoo of too many variables. So I do need to analyze this px and px3, and then x operator. So the question about commutation comes from the following consideration. We do suppose we are doing science for a living, and our income depends on force. It's typical that there will be reviewers who will try to find, to grade us negative, to find weaknesses that we need to prove that we right. So we need to find if the approach that we're doing performs well in known circumstances. And one of the ways is to check if the operators of position and momentum obey the commutation relations. If they do, we are on a good way. If they do not, we better hide it from the viewer or promise to do better. So we want to take this package commutations of the method, and especially the final one, highly likely will be attended by visitors who will either give positive comments or criticize. And doing things like that is a weapon to resolve that. Okay, so mesh px. It doesn't want to show because px is imaginary. If I do real px, start new figure. Okay, it's already here. So it is a small number, it changes. So real part is small and boring. If I do imaginary, it shows much bigger values, and it has main features near the main diagonal, as it should be for momentum iterator. So I didn't start the commutation yet. So now let's do px3. It looks very, very similar. So I'm doing an image of the same operator, but defined in a different way. So it has some oscillation near the main diagonal, but it protrudes to the smaller number of subdiagonals. If I do real px3, it's better. It's closer to 0. It looks like better definition. Now we also have the hop. What is hop? Yeah, X operator. Make sense? Or you think it is ugly or senseless? Only diagonal elements increase in value, and all others are zeros. And if you do imaginary, then it is absolute 0. Now, we may want to practice multiplication of these matrices. Like if you multiply x by px3 minus px3 times x operator. So it is a commutation, right? Multiplication with swapped order. And it may refuse to plot because it is imaginary stuff. So we need to plot real and imaginary again. So real shows nothing. Imaginary, let's see. It shows almost nothing, but on the right in the middle, near the main diagonal, it shows a thing that is close. Huh? Close. Pardon? Near the main diagonal, it shows the feature. I'm going to change the axis. This automatic axis. How better type it manually? Axis. So x will go from 0 to 200, y will go from 0 to 200, and z will go from -1 to 1. So we do see that there is a feature on the main diagonal. It is imaginary and it is the same everywhere. So what is the matrix that is equal to 1 on the main diagonal and zeros everywhere else? No, momentum has minus ones and ones. And if you have only ones at the main diagonal, it is identity matrix. So by multiplying, insert new slide. So if you do have a matrix that has 1, 1, 1, and everywhere there are zeros, if you practice row by column by multiplying such matrix on arbitrary vector, row by column, so it will be A, row by column, it will pick up B, and if you do last one, it will be C. So identity matrix will produce itself. So by practicing this x times p, x and p operator, we are getting identity matrix multiplied by point by half, and it is imaginary. But how should we interpret it? So if this commutation is not zero, means that position and momentum operators do not commute. Their commutation should be equal to like Planck constant multiplied by identity operator. If operator is equal to constant, it means it is constant by identity operator. And what is a little strange and a little worrying is that absolute value. I would expect if everything would be perfect, it will go to 1. But general trend is not as bad. One can try to compute some other operators, but this test is really worth of trying. And if you can reproduce this little experiment and provide background, what it means, it would be helpful to the whole class and appreciated by visitors, if any. Okay. While sitting here, you may copy paste whatever you do and put it into your PowerPoint to save you time later. Okay, let's check where we are now. Summarizing quantum dynamics in form of movies and uploading to YouTube. This is the easiest thing, and let's do it right away. So in the email week ago that I did just resend, there were 2 codes. One that has the word comments in the name, and another that doesn't have word comments, like new. In this new one, you recognize it has this video object, and basically it is the same code, but in the middle, it to the place right after the end of the loop cycle. It has the stuff that you already saw. Current frame equals get frame, write video, video object, current frame. If you run the stuff, and you can run it right now, I did run it just before we started, in the space, in the disk space where I'm running this code, there appears a file with packet mp4 with packet.avi. So I can go to YouTube and upload for this file. So I just need to find where I am. So downloads with packet, uploading example for CHEM364. Next. Next. Public. Publish. And it should be ready. Right? So this is a skill that is needed for everyone in the class. Subsequent homeworks and project will include task of uploading stuff into the YouTube. So let me quickly share this recording with everyone. Okay, so you will be able to teach others. Good. Let's check this. Let's check with Connor and Spencer. Any specific questions right now? If no, I'm going to continue. So, modeling quantum dynamics of an electron, initial conditions. We covered this last time. Initial function is chosen as Gaussian. Oh, we covered alternative methods to do quantum dynamics and initial conditions in case it is available in the recordings of the previous meeting. But I'll quickly navigate to the right spot in the so line 66 defines initial condition from where we start. So one needs to multiply Gaussian function to be certain about position of the wave packet and multiply plane wave in order to be more or less certain about the momentum. These two factors depend on two constants, x, well, more than two, but x naught is initial position, p naught is initial momentum, line 66. And if we are looking at the very beginning of the code, line 5 and 6, one can define these values there. So those are values that we will be continuously modifying as we run this code, not only for the project, but there will be like 1 or 2 homeworks. Okay. Initial conditions done. Discrete representation, wave function in space and time, normalization. Oh, normalization. I'm going back to the line 66. Line 66. And note there is a square root of dx, which we didn't have in class. So the square root of dx is inserted because we are doing everything in the numeric representation. So if you do have wave function and we want to normalize it to find norm, we integrate multiplying by dx. if our wave functions are represented as values at specific points, psi sub I, summation over elements I, it will never be equal to n because we are missing this dx. In order to make bridge between continuous and discrete, we are defining this discrete wave function, psi I discrete, same way as we were defining the continuous wave function, but we multiply it by square root of delta x. Then by multiplying it by itself and practicing summation, we will arrive to the same normalization. Make sense? And this, let's check for whom was this information. Normalization, it was intentionally for Jared. Jared, if you're watching the recordings, listen 1 minute before me waving the hand. Size of simulation versus time of simulation. Okay, now in next 5 minutes, my client is Jared. So I'm going to rerun the code again. Okay, erase the figures. Otherwise, it is too busy on the. Okay. So let me increase the momentum P naught. So right now it is 0.25. Let me increase it 10 times, so 2.5. Note that simulation cell has borders left and right. What would happen if the momentum is so high that during the simulation time it should go away from the room? What would happen? What do you imagine? Should it? Huh?
Would it go way up?
There are two options. Normalization is preserved, so we cannot have it completely disappear. Although hypothetically it can show like blank and nothing, but it could either reflect if you put a wall, or we can set up so-called periodic boundary conditions. It means like if by exiting this door, I immediately reappear from this wall. Right? Or if I go this way, so it is kind of Möbius ribbon connecting these two pieces of space. So save and run. So note I did set up velocity 10 times bigger than before. Let's forward, and 3 appears from the where it left. And 3 appears again. So what is useful to look in the output figures, I would like to bring your attention to the image right here. It has position and time, and we can redo this figure standalone without other panels, but I'm kind of in rush, so let's focus only on this. So I'm looking only on the lower panel of this figure. Maybe on screen. Well, so we did this way is better. So position and time. So we do start with x near 30. And then as time passes by, the position increases. As it reaches the border, it disappears on the top and reappears on the bottom. This little trick will not kill the code. Code is ready to work in this environment. But for our brain sanity, it may be not good. So if you want to avoid this effect, there should be a condition for the size of the box, simulation box, and velocity. So velocity times simulation time should be smaller than the size of the box. And those parameters can be controlled at the very beginning. So m tau times tau will be simulation time. P naught is the momentum, velocity, and the size of the box. Let me check what it is. Number of points times dx. Number of points 200 times dx. One is here, but it is coming into no.
Right above the 100.
Oh, okay, yes. So size, okay, we have size settled. But by relation between these parameters, we can avoid this unnecessary effect. And later on, if you saw the schedule of today's meeting and of presentations, there is a plotting of observables versus time. If you plot expectation value of position versus time for this free particle in space, it is expected to linearly grow forward, right? But if you do have this strange thing, then you see here it drops instantaneously. So it approaches almost 100, then it drops back to 0 and then starts growing over again. So it is not actual scientific, chemical, or physical effect. It is a shortcoming of this periodic boundary condition, which is a like full proof of the code, just in case if we set up too high of the momentum. This was a message for Jared. So it was size of the simulation cell versus time of simulation. Now, for unknown presenter, number 5, accumulation of expectation values into blah, blah, blah. So I do not know for whom I'm speaking right now, for unknown attendee of the class, but well, we all need it later, so it's not worth it, I'm sure. The goal of the class in this little conditional modeling is to help real experiments, to predict or interpret observables. But in order to predict observables, we need to compute. We need to convolute wave function that we are finding here with operators of observables. As a guinea pig and little toy, we need to have position implemented, but later on we can design different observables more related to experiment. So we need to compute expectation value of an observable at each step of the trajectory, and then save it in a specific array of data to be able to plot. So we already practiced. We already used it as users. We were looking on this expectation value of position as function of time. Now we need to look which part of the code does it. Okay. And there are other things like momentum and width of the wave function. I'm just a little impression. If you look how broad this wave packet is, it should it width should grow quadratically for free space, right? We put it in the class. And here it shows that yes, it grows quadratically, but sometimes it goes to infinity and then drops. It is an artifact of the periodic boundary condition. When it approaches the wall, half of the packet is there, half is there. Means it has infinite width. So if we do not want criticism of reviewers, we should apply this code in the shorter times or use bigger blocks. Okay, so how to find the spot where the expectation values are computed? We need to go to the end of the loop. So loop starts at 164, and then there is a little line that helps us and guides us until we are done with this loop. In other versions of the code, near this end of the loop, we have the block for making movies. And most of the code is devoted to computing observables. It's most lengthy part. So, for example, this line 232 AP3 gives the wave function computed by method 3 multiplied by momentum operator computed by method 3 multiplied by wave function computed by method 3 divided by normalization. So since MATLAB does have this scalar product, this product of the stuff with apostrophe and without apostrophe, its scalar product that automatically means summation. Or integration. And since our normalization is already included as a square root of dx, this line is expectation value of momentum by method 3. Whoever is interested and need for presentation, ask me what is method 1. I'll just skip it intentionally to save time. It is the easiest one, and we will not use it for projects. Okay, now this letter A for average, AP3 is computed once when we are in the loop. If you come through the loop again, it will override the content of this variable. So we need to accumulate the data. So in AP3, this line 235 accumulates the values of AP3 along the trajectory. So we need to declare at the beginning of the code the variable average P3, which is average P3 equals just empty rectangular bracket. It's like array of 0 length. And then each time we are coming through this line 235, it creates a column of data where previous part of the code with so many elements is adding one element that was computed just before. And each time we are passing through the loop, the length of this column becomes bigger. If we have like 700 times steps, it will be a column with 700 elements. So let's look if I was lying or not. So size of AVE P3 700 and tau number of time steps. If I just Now I'm doing a silly thing. So it just plots so many elements. Now we see that it is basically real, which is good. Momentum is real. But as all variables here, it has imaginary part, although it is 0. So if I want to plot it, I do figure, and then plot AVEP3, and I want to plot only real part, otherwise it will come back. Well, we have some value which has small numerical error, but it doesn't change with time. Is it a surprise? No, we covered it in the Ehrenfest theorem that in free space there is no force that would change momentum of an electron. So it's quite expected to result, although a little void. Right? So let me double check who is presenting it for whom. Oh, unknown presenter number 5. Now, if we do want to do position, this position, it is a little bit easier. So since position operator has only diagonal elements, we do not need actual wave functions. We can take probability distribution, multiply it by this position operator, and make summation. So AVG will be the expectation value of position. Now, if I want to accumulate the data, I do the same thing, right? So let's plot this AVGS, which is expected to be AVGS. So it grows linearly, then it drops because of periodic boundary conditions, then it grows linearly once again. So we are saving numerical data into files for separate analysis. This part, maybe let's check after end. No, it is not saved, but if I want to plot this data not in MATLAB, I can just type save minus ASC II AVGS AVGS. And then in the on the desktop file browser, I will see this set of data that I can use later to plot with Microsoft Origin or Excel, whatever I like. Okay. Spencer. Now thanks for Spencer. Are you on the? Let me check if you. Yeah, Spencer is here. So visualize real and imaginary part of the wave function. So in some sense, your part is already shown here in the little image at the lower right part. So let me go to the figure and MATLAB. So plot psi2. What do I get if I hit enter? No, I'm going to get error. Likely. Or it will show maybe not error, but something what I do not want to see. Exactly, exactly, exactly. So then we need to plot three, maybe plot three time real and then imaginary. And time is not defined, but I can fix it later and plot this helix. Huh?
How is your time?
No, tau is increment of time, and we need an additional column. But if I plot real, it shows it's still ugly. Okay, if I plot imaginary, it is still ugly. Oh, not tau. I need to plot x, but let's fix it later. If I plot, yeah, x, very good. No, not time. Also, so it is a helix or like a little chalice, right? But it still looks a little ugly for analysis. What if I do plot x, comma, real, x, comma, imaginary? So now it shows that real and imaginary part, they oscillate with slow change of amplitude, and they are shifted in respect to each other by half phase, like sine and cosine, which is expected for imaginary exponential. But we do need absolute value of the wave function rather than real and imaginary part. This is more realistic. So if I do either probe 2, which will be psi squared. No, it doesn't want. Okay, I'll do real psi 2 squared plus imaginary of psi 2 squared, and then I need to take square. No, maybe I didn't need square root. It makes. Oh yes, I just need to put x here. Good. So if I do, let's look at what I do. So real part, like cosine squared, imaginary part, like sine squared, then added them together, which should give one with the pure plane wave, and then took square root. So it shows this yellow envelope function, and people, the envelope is a colloquial word because this slowly, quickly changing functions are enclosed in the envelope. Okay? So envelope function is very slowly changing, and it shows maximal value of the either real or imaginary part of a function. So these three lines is the most adequate representation of the wave function, although not very pleasant for human eye, but it is the helix is maybe too much for humans, but this is most standard and most adequate representation of wave function. If it one-dimensional wave function has non-zero momentum, it is always have negative imaginary component. And to represent wave function, one needs to put both real and imaginary part. Since it is not always easy and pleasant for humans, the standard way is to complement this real and imaginary part by the envelope function, which is this real and imaginary, or add comma x comma so there is one more line which is less intense. It's probability distribution. So it is what would be without square root. Why square root is taller than wave function square? Because it is smaller number, smaller than one. Like square of the yellow will be purple. So square of 0.1 will be 0.0. Let's check. Go to Zoom and check chat if yes. So I need to check with Spencer. So Spencer, please confirm if this little story did make sense, and express any questions about this content, because it is it looks like it is your selection for presentation. So makes sense. And if I have questions, I will remember. Okay, very good. So let me check what is the next. Visualize real and imaginary parts of the wave packet. So we're done with this. Visualize potential and probability distribution. Why there are three of them? It's because there are three methods to compute wave function and three ways for probability distribution. One may want to put three of them. Potential. For it is not very useful right now, but I will better show it so that we feel better next time. So plot V. And right now it shows like just straight line. V is potential energy. If we look and let's look it through the code. So we have V is equal 0. But in this line 60, we can comment it out and set up different feeling, different content of the variable V. And then this plot V will be different, and the whole code will work different. For example, if I comment this one out, comment, I don't remember literally what is variable 2, but okay, yeah, now I know. I'll save it and rerun it. So it has potential which is different from free space. You see this V is a different thing, and wave packet passes through it because we did set up too high velocity. So it's not as interesting. If I simultaneously set up the smaller value of velocity as we had before, 0.25. Save and run. So now when it hits this barrier, it tries to pass through, but it kind of reflects from it. And then it goes back. In some sense, this little thing is the closest to real life in the whole course, and at least at this stage of development. So this situation when potential represents lower area, and lower area once again corresponds to transition state chemical reaction with reactant, transition or intermediate and product. And wave packet corresponds to an attempt for reaction to go over the barrier. So this is, I was answering to how to plot potential, but it also relates, just a second, relates to the very last question. So just run the code with several different potentials and report observations, whoever selects it. Yes?
So you open up pump, you do more velocity, so the velocity corresponds.
Exactly. You are ready to get hydrated, be done with the course. Kinetic energy of each molecule added together with some with temperature. So momentum squared basically is temperature. The higher the temperature, the higher is momentum. Excellent. Okay. Let's look what else we have. So visualize any observable. We already done it. You just look for this something average and plot it. Organization of data, bundling groups of observables. I understand what I'm asking about. If you look through images like this, they are pre-made with several lines and several panels. So if one looks into the part of the code right after the loop is done, I'll tell what so after line 245. So it goes through this figure, subplot, and then it combines this x probability to x probability 3, x and potential. So it plots subplot is a panel, and when one has this segment of argument and function, it plots several lines in one plot. And then it gives some labels, and we can see it. Time, expectation value of position. Time, expectation value of position by different method. Time, expectation value of position by theory. I believe it is this one, and it has some other comments which we can maybe just erase, but it shows expectation value of position by one method, red, by another method, blue, and dashed line, prediction of theory. So just bundling is a way to analyze stuff simultaneously. If one writes a report, bundling of data into one figure could be needed. So bundling groups of observables. Let's check with Spencer once again if these things make sense. Spencer, okay, yeah, thank you. Then I'm going to the next one. Or we already covered it. Computation of expectation values, position and momentum. Yes, we did it. Expectation values of energy and uncertainty of position and momentum. This is needed, and I think we are doing well this time. I plan to finish by 7, and we are really really quick. So, expectation value of energy and uncertainty of position and momentum. Okay, I'm going to focus on line 218 and 220. Insert, useful. So suppose I am having this probability times x dx, and that integral, and it gives me expectation value of position. Now I know the center of the expectation value of the distribution, somewhere in the middle. And by the way, in freshman chemistry, there was a lot of thermodynamics. It will be much more in the next chapter of physical chemistry, right? Next semester. So you speak about distributions and probability from different aspects. Now, what if I redefine this x operator in the following way? I will do x minus expectation value of x. Zain, what do you think? What if I multiply this new operator by the function squared and do dx? What will be the answer? No. If this is x, it means if I subtract, it means I pull the y-axis and redefine system of origin. So now it will correspond to the center of the distribution. So in new system of coordinates, this operation will give 0, right? Because the values will be randomly to the left or to the right from the center. But if I want to assess the width of distribution, how far the values can go from the central line, I do not want them to have negative values, but I can put little square here, and then it will be always, I'm kind of mirror flip this stuff into here and add them together, right? So this procedure of x minus average x squared is called variance. And in some sense, it is what we put on in the denominator of exponential power in the Gaussian. So if it is Gaussian function, the result of this operation will coincide with what we put in initially. But if it developed and changed shape, they may deviate. And from the third point of view, it is uncertainty of position, right? So if wave packet is a peak, very sharp peak, then this uncertainty will tend to 0. If it is shapeless and fat, it will be bigger. So we need uncertainty because there were some theorems and how good we know where it is. So it is uncertainty of position. Let me go back to the code. So the line 218 shows this x minus average x squared times probability. So it's implementation of this variance. And then when we do variances, we just accumulate it. So if I go into the method, open new figure, and plot variance. It shows approximately what we expected, quadratic growth of the width. So we are done with uncertainty of position. Now let's do uncertainty of momentum. I'm returning back to the PowerPoint and inserting one more slide. So now we have momentum operator, wave function with star, wave function without star, dx integral will give expectation value of momentum. Now if I redefine momentum minus expectation value of momentum, psi star psi dx integral, this should give 0, right? In the same way. But if I put square in here, it will give the uncertainty of momentum, variance of momentum. So let's look onto the code. So AP psi prime px psi. So it is expectation value of momentum. ASP is px minus AP, which is already expectation value, will be the here it is labeled as standard deviation of momentum, but we can call it uncertainty of momentum. Average SP is where it is accumulated. So, accumulate uncertainty of momentum. So if go what VSP. So probably I should do real. So it shows big value, which probably corresponds that a lot of plane waves, contributions, partial plane waves with certain momentum, contribute to the width of the momentum in the momentum space. And we can compare if the same stuff with third method will give the similar results. So VSP3. Yeah, the third method, which is more reliable, gives also gives similar results. So we can analyze uncertainty. We can analyze their product and see if uncertainty relation will be proved or disproved here. Let's check what else we need to do. Expectation values of uncertainty position momentum, expectation value of energy. Basically, for expectation value of energy, one needs to plug in the Hamiltonian in the middle of this expectation value procedure. Here, line 154, line 155. Since the system is isolated and total energy is not going to change with time, I believe it is a constant, so it is only numbers E3 and E2. Those were results for barrier. Therefore, uncertainty is big because after it hits the barrier, and energy is negative because there is a negative range where it comes over the barrier. Okay, makes sense. What else? Application of wave packet code to box, to barrier, and to harmonic oscillator. It's a second choice of Spencer, and I hope there will be more participants of the class selecting, but let me quickly do it. So at the beginning of the code, there is segment between lines 55 and 60 for definition of the potential. So let me check what is our barrier one. What So just to be quick, I can put minus sign, and then it will be a barrier, like a dip instead of barrier, and then it will be a box. Also, I can put X node in the more to the middle. Save and run. So the barrier is not very deep, but it kind of stops and forbids it from going too far. And part of the wave packet is trapped above the barrier. If I do the just make the barrier 10 times deeper in line 55 and rerun stuff. It has bigger strength to retain, to attract electron inside this barrier. And if I make the walls infinitely high, then it will be more particle in the box. So what else can we do? And the another sub question was if we make harmonic oscillator. So line 58, I just uncommented. And then the wave packet is trapped in the harmonic oscillator and it starts oscillating forwards and backwards. So whoever will be presenting last subject may want to make this 3 examples and briefly cover the trends. So one little thing before we depart, I don't know about you, but I really like this colorful image in the panel, which shows this oscillations or propagation of the wave packet. So when possible, the best way is to plot movie. But if movie is unavailable, another way to represent dynamics of wave packet is to make this two-dimensional, three-dimensional map for x, y, and the probability. So it is variable s, just s, and s3. So we accumulate probability computed by third method as a row in a matrix, and in the lines 240 and 241. So this S3 is accumulation of probability at each slice of time. So if I do figure, and then do mesh S3. So it shows this stuff, how the distribution moves in space and time. And it is one of the ways to summarize the results of the code in a single figure. We will be able to repeat it.
I was messing with the heat chart. No, the heat chart.
Uh-huh.
I was just, see what you had to say about this. So there was, so we have this looks like it fits along with flex, or is it going to? So we open, let's open the figure and do mesh just all that S sent for this method. So there is another, let's see, restriction. When the peak of the reflector becomes bigger than the size of the box, the simulation also loses in yeah.
And one of the features of the harmonic oscillator is that it retains not only the position within frame, but also the width, because it's reflection. So I'll stay here and answer any questions. Let's check if there are specific questions from Spencer and Connor. So I'll stay here, but I believe we went over all subjects, and it seems whoever attended the meeting and watched or will watch the recordings will be 100% ready for presentations. So Spencer and Connor, please let me know if you have any immediate questions that you want me to address right now while I'm here in front of the computer and camera. If, okay, yeah, thank you, Spencer. What about Connor? Okay, so just plan on if you were following the exercises, especially related to your subject, just plan to make screenshots and copy paste them in PowerPoint. And I will ask everyone to send slides by Sunday night, so that on Monday they are ready. Okay, I suggest we disconnect and complete the session. If there are any objections, I'm not in a rush. I can stay longer, but I do not see objective reasons.
It's just you and me. And
Yeah,
Brian O'Flynn. You want to go over the directed slide?
Oh, let me stop recordings. Just, I think everything was. We're not going to speak about anything sensitive, but just in case